Welcome to NGA's AIA presentation, Reflected Solar Energy of Glazing Systems in Buildings. The National Glass Association is a registered provider with the American Institute of Architects. Please share your AIA member number and contact information on the sign-up sheet or post-session assessment to ensure you receive credit for your participation. A certificate of attendance will be sent to all attendees. This course is designed to educate architects about the impacts of solar energy as it's reflected off buildings. It will offer design considerations to reduce the possible effects of the reflective characteristics of exterior cladding materials and glazing systems. Environmental, architectural, and material elements will be discussed with regard to how each impacts reflectivity levels. Upon completion of this course, you will be able to identify the impacts of solar energy reflected off buildings, list at least 3 environmental considerations that can reduce reflectivity, list at least 3 architectural features that impact reflectivity, describe design considerations to reduce effects of solar energy on exterior materials and systems, compare environmental, architectural, and material elements and their respective impacts on reflectivity levels, and discuss additional glazing considerations that can influence reflectivity. The study of light is subjective in some aspects, like glare, but very objective in aspects like direction and reflection. Basic optics laws tell us that when a light ray encounters a glass surface, part of the incident ray is reflected, part is absorbed, and the rest is transmitted to the other side of the glass. Reflection produced by glass and other smooth and polished surfaces is called specular reflection. The reflection from rough surfaces is called diffuse reflection. The reflected light directional behavior is described by the reflection laws and shown in the figure above. The incident angle is equal to the reflected angle. The incident ray, the reflected ray, and the line perpendicular to the surface, the normal, are located on the same plane. We must remember that sunlight is comprised of different components: ultraviolet, or UV, visible light, and infrared as shown in the figure above. The phenomenon in which light is reflected off exterior cladding materials back into the environment is called solar reflectivity. Note that sunlight reflected off exterior cladding materials carries all 3 components of sunlight. Building design professionals must account not only for solar reflectivity, but also for design criteria to meet building code, industry standards, design intent, and desired energy performance. Environmental conditions and geographic features play important roles in how both direct and reflected solar energy can affect building cladding materials and fenestration components. An important consideration is solar geometry and how it changes throughout the day or year. Direct solar radiation is dependent on the sun's angle and geographic location of the building. The figure above depicts an elevation view of representative solar radiation geometry for neighboring structures. Angle of the sun can play a role in how much reflected solar radiation is reflected onto adjacent surfaces. The peak solar irradiance in the U.S. for a surface perpendicular to the sun occurs when the sun is highest in the sky. As the angle between the sun and the receiving surface increases, the effective solar exposure is reduced. Normally, for a high summer sun, low solar irradiance occurs on a vertical surface at midday, and high solar irradiance occurs on a vertical surface shortly after sunrise for an east-facing location and just before sunset for a west-facing location. For a low winter sun, high solar irradiance occurs on a vertical surface usually at midday for a south-facing location. Almost as important as direct solar radiation is reflected solar radiation. A percentage of incident solar energy is reflected from all exposed building materials. Many common building materials are optically rough, so the reflection is effectively diffused in all directions. The figure on the left shows a plan view of representative solar radiation geometry on parallel walls, representative of neighboring structures. And the figure on the right shows a plan view of representative solar radiation geometry on perpendicular walls, representative of an alcove on the same structure. On smooth surfaces such as window glass, accumulated snow, and swimming pools, the reflection is direct and its path is determined by the angle between the line normal to the glass surface and the Earth-Sun line, which is a combination of the solar azimuth and solar altitude. This is called the incident solar angle. There could also be a cumulative effect, where surfaces can receive both direct and reflected solar radiation. Building materials can be damaged when heated above their thermal resistance rating. Variables other than direct and reflected solar radiation could impact the amount of heat transfer to a surface, such as local climate conditions. Wind speed and air temperature can affect the heat transfer rate of a surface. Physical obstructions, such as foliage, fences, or adjacent structures, may block direct or reflected solar radiation from reaching a surface. Long-wave radiated energy received as re-radiated heat from nearby surfaces, such as asphalt, may increase the temperature of a surface. And proximity of alternate heat sources to the surface could provide direct or reflected radiation, such as air conditioner compressors and barbecue grills. Architectural design, such as alcoves, overhangs, inside corners, and other features may block wind or trap heat that could affect the surface temperature. The surface properties of building cladding materials and fenestration components influence the degree of reflected solar energy. As mentioned earlier, the optical smoothness of a reflecting surface affects the amount of direct solar radiation reflected to other surfaces. Optically rough surfaces, such as painted walls, patios, sidewalks, and driveways, provide a more diffused reflection onto adjacent materials. The color of a reflecting or receiving surface can also influence the effect of reflected solar energy. Darker colors will tend to absorb more solar energy rather than reflect it, and vice versa, light colors could reflect more solar energy than they absorb it. Many building cladding materials and fenestration components are designed to reflect solar energy to either provide better performance, specific appearance characteristics, or improved longevity. These types of products could provide for more direct reflected solar energy to adjacent materials. Building materials such as aluminum and copper flashing, brass kick plates on exterior doors, coated and non-coated glass products, aluminum or vinyl siding, and painted wood, to name a few, can and do reflect solar energy onto adjacent materials. Now let's take a quick knowledge check to confirm your understanding of what we've covered so far. Type the link as it appears on the screen into a web browser, or, using the camera feature on your cell phone, scan the QR code on the following slide to access the page. We will allow a couple of minutes at this time for you to complete the knowledge check, answering the 2 questions that appear on the screen. The environment in which the building is located and the incident solar energy both influence heat absorption. Depending on the building's geographical location and the time of year, the intensity of solar radiation and the resulting ambient temperature can vary significantly. Furthermore, wind speed and the reflectivity of materials in the surrounding area also affect the temperature of building materials. As an example, direct and diffuse solar radiation can raise the temperature inside the insulating glass unit and affect its level of deflection. The level of solar radiation incident on the surface is defined by the combination of its orientation, the solar azimuth, and the solar altitude. At high sun angles, greater than 40 degrees, the type of glass used could have significantly less impact on the reflectance of the IGU. Environmental factors play an important role in how much heat is absorbed by materials, as well as the flexing and deflection of IGUs. IGUs typically have a sealed gas volume and contain an atmosphere representative of the air temperature, altitude, and atmospheric pressure of the manufacturing location in which the unit was sealed. Atmospheric conditions can change regularly, meaning the built-in air pressure can vary from unit to unit. Of more importance is that when the unit is installed in its intended location, any change in the pressure balance between the sealed internal volume and the atmosphere will result in glass deflection. Therefore, changes in temperature, pressure, or elevation will produce some distortion in the unit, which can be considered normal and not necessarily indicative of a defective unit. As an example, when atmospheric pressure increases relative to the sealed interior pressure, the glass can deflect inwards and become concave. There are 5 main factors to consider in building design: building location, building orientation, material selection, building design, and exterior building features. A building's geographical location affects the amount of available daylight. Locations between the equator and the Tropic of Cancer in the northern hemisphere and the Tropic of Capricorn in the southern hemisphere have a more balanced day-to-night duration. Locations further north or south from the tropics see a more drastic change in daytime duration between seasons. A building's geographical location also determines the solar altitude, which is the angle between the horizon and the sun. Locations such as New York and London are subject to low solar altitude angles during the winter. Their 41 degrees and 51 degrees north latitude, respectively, can be a design challenge when trying to keep direct sunlight out of buildings. Building orientation is one of the main factors to consider when trying to address solar reflectivity. It is of common knowledge that south exposure facades are subject to direct sunlight during the largest part of the day for projects located in the northern hemisphere. However, east and west-facing facades need to be carefully studied due to the relatively low solar angle at sunrise on the east facade and sunset on the west facade. If properly oriented, even the most challenging building geometries can be accommodated without generating more solar reflectivity. There is a wide variety of materials available and being used in the design of buildings. These materials are now mixed on different building elevations in order to achieve the desired appearance. Some materials are available in different textures and finishes. Others have the ability to meet different performance criteria. But the most important factor to consider is the selection of materials in the context of the entire building. When using reflective or potentially reflective materials, the designer must carefully study the building context and decide what materials serve the intent without compromising performance and the final outcome that could be produced by such materials. Some reflected materials can be treated to become less reflective. Materials like glass are available in a broad palette that allows the most complex building geometries to be achieved. Building design should bring all the factors mentioned above into harmony. If the building location and orientation are carefully studied, environmental factors can be designed for and building materials selected properly. Many times, there is no single factor to blame in the design of buildings which have issues with reflected solar energy. Factors mentioned above in combination with building design are the common denominator in most cases, which have unfortunately made the news. Concave facades pose a major challenge in the selection of materials as they may focus reflected solar energy. Focusing solar energy can lead to glare and increased surface temperatures at the focused areas. Materials for these types of building geometries need to be properly selected and addressed for the different outcomes they might produce. Special attention must be paid to south-facing concave facades, since, as mentioned above, they are subject to the sun's solar energy the majority of the day. Reflective materials on concave facades can exacerbate the end result if overlooked during design. One example is the Vdara Hotel in Las Vegas. The curved concave design reflected the sun and increased temperatures in the pool area, garnering media attention until the effect was mitigated with umbrellas and non-reflective film. Exterior building features can help mitigate any potential solar reflectivity concern. The features are oftentimes mounted to the facade or can be directly attached to the building structure. Features such as shading devices, fins, and decorative designs can be seen on buildings around the world. Some of these features serve a performance purpose, while others are only aesthetic. Cladding materials include siding, brick, stone, and more. The ability of cladding materials to absorb and reflect infrared radiation varies depending on several factors. First is the material type itself that is selected. The material's color, in that lighter colors reflect more than darker colors, and the material's surface finish. Shiny or glossy finishes reflect more than matte or textured and flat finishes. If a concern exists regarding a cladding product's exposure to infrared solar radiation, then a specifier of a cladding product should take these variables into consideration when designing for proper performance and longevity. Now let's take a quick knowledge check to confirm your understanding of what we've covered. Type the link as it appears on the screen into a web browser, or using the camera feature on your cell phone, scan the QR code. We will allow a couple of minutes at this time for you to complete the knowledge check, answering the 3 questions that appear on the screen. Light and solar energy incident on glazing will be partially transmitted through the glass, absorbed by the glass, and reflected off the surfaces of the glass. The degree to which light and solar energy are reflected are dependent on a number of variables. These include the angle and orientation of the sun to the surface of the glazing, the flatness of the glazing, and any coatings that are on the glazing. Glass may deflect due to a variety of environmental factors that may lead to the concentration of this reflection in a localized area. Such deflection can occur in monolithic glazing systems, but it is more typical of insulating glass units. Perfectly flat, uncoated glass will reflect light and solar energy. The effect of the environmental factors on glass deflection can be influenced by a number of design considerations. Thinner glass will deflect more easily than thicker glass. Whether heat strengthened, tempered, or annealed, all glass types will deflect the same. Large IGUs will deflect more easily than smaller units. The aspect ratio of the height to width or the width to height of the IGU can affect glass deflection. Aspect ratios closer to 1:1 or a square will have greater deflection than units with higher aspect ratios. IGUs with a greater distance between glass slides that define the cavity gap or airspace will have greater deflection than units with narrower gaps. The following design considerations are some of the possibilities to reduce the effect of solar reflection. In building design, consider using materials that are able to resist temperatures greater than 250 degrees Fahrenheit. Be aware of building areas of high risk for solar reflections and determine if any building materials in the vicinity will contribute to increased heat gain on other building surfaces. Walls with highly reflective surfaces that are directly opposite other walls or inside corner details should be evaluated. Other areas include alcoves and overhangs. Be aware of building orientations and how direct solar radiation will potentially reflect off the building surface when facing south, east, and west. Be aware of curved walls or concave facades that may have a concentrating effect of any reflected solar radiation. Be aware that features near a building, such as swimming pools, accumulated snow, and concrete, can reflect solar radiation and contribute to the amount of solar radiation encountered by the building surfaces. And be aware of how building features, such as shading devices, fins, and decorative designs, can reduce solar radiation reflectivity. For residential windows and doors, choose NFRC certified products where possible. NFRC requires that manufacturers meet tolerance criteria for insulating glass gap dimensions at the point of manufacture, which correlate to glass deflection limits. Capillary tubes have been used to control the flatness of the IGU, but they may negatively affect thermal performance and shorten IGU life if not properly closed at the final destination. Special considerations should be taken for their use, especially when there is low-E glass and argon fill involved. Please consult with your IGU fabricator for proper procedures for closing capillary tubes and installing IGUs with capillary tubes. Be aware of how glass thickness, IGU size, aspect ratio, and cavity gap dimension can affect the ability of an IGU to deflect easier with barometric and temperature changes. Be aware that all glazing options, both coated and uncoated, will reflect solar radiation to some degree. Other cladding materials and adjacent surfaces could have similar or worse reflective characteristics. In review, you should now be able to understand and achieve the learning outcomes listed here. Thank you for attending this AIA presentation, Reflected Solar Energy of Glazing Systems in Buildings.